Lesson 20, other components. Well, we will discuss the other types of components in a circuit. So we've talked about, when we talk about circuits, we've talked about the battery, we've talked about light bulbs, we've talked about resistors, we've talked about, switches. These are our standard things. Then what we've talked about yesterday is we talked about diodes. And so I guess what we want to do today is talk about these other ones. Oops. What are these other components that we don't normally talk about? What did we do last lesson? The last lesson was pretty full on. We did three major things. The first thing we did was we answered this question first. And then we did some measuring circuit properties. We use an amp meter to measure current. We use a voltmeter to measure voltage. Amp meters must be connected in series. Voltmeters are connected in parallel around what we're trying to measure the voltage. We talked about how you read an amp meter, a little bit about how we have multiple scales because you can have circuits at different points. And I talked a little bit about this idea of maxing out a scale. You can max out a scale. This is maxed out at, in this case, 5 amps, but it could be more than 5 amps. We don't know because the scale is maxed out. Then I got you guys to, we talked about why it has to be in series versus parallel. We talked about short circuiting things and students destroying amp meters. Then I talked about why do we use an amp meter if we can predict things? I said, well, the main reason is because non-ohmic devices don't follow the rules. Ohmic devices, well, if you increase the voltage, the current goes up. Wow. Look how straight that line is. Holy crap, I'm amazing. Sorry. Yeah, the idea can't get that on the whiteboard, ladies and gents. Observe the beauty. Yeah, so the idea is that the current, as the current goes up, the voltage goes up, and as the voltage goes up, the current goes up. You give it more energy, and you don't change the resistance. If you give it more energy, those charges are going to move faster. That's what the lesson here is. That's what an ohmic device is. That makes sense. But with a non-ohmic device, you end up with something that looks more like, and this is not going to be as neat, something like that. See, it shouldn't curve back on itself. And that's a non-ohmic device. There are other non-ohmic devices that you can get non-ohmic devices that look like, they start off looking like a ohmic device, but then they do something like this. It's actually, this is what happens with incandescent bulbs. It's like, oh, you put all this extra voltage in, but it doesn't actually lead to a thing. But the main thing is it's not linear. You're putting in all this extra energy, but it's not making the electrons move faster. So that's what you want to look for. Non-ohmic devices are non-linear. And then we did some examples. We looked at some exponentials so you can get an idea of what an exponential looks like. Then we talked about diodes. These were our first non-ohmic device. The diode is a one-way component, therefore it only allows current to go through one way, left to right. That's why it's called biased or right to left, depending on how it's shaped. An LED is a specific kind of diode. It glows. It's a diode that happens to glow, and it doesn't follow Ohm's law. It has a switch-on voltage. So when that means that instead of going up and up and up, essentially you increase the voltage. When you get to a certain point, maybe 2 volts, it'll then go, oh, well, then I'll switch on. And it pretty much does that. You actually see that here, right? When you reach 2 volts, like for example, this blue one turns on. When you reach 1.6 volts, the green one switches on. We call that a switch on voltage. And what's interesting with diodes is they will always drop that same amount. So a diode will, it doesn't, if you go for 100 milliamps, you go for 1,000 milliamps, they'll probably only drop about 2 volts or something. Whereas the other ones will scale linearly. These ones just sort of don't really scale. We looked at 3 examples. And now what we're going to talk about today 5 examples, sorry. And what we're going to talk about today is we're going to talk about other components. So what else is there? What other non-ohmic devices are there? Are there other non-ohmic devices? And in fact, there are other non-ohmic devices. Other non-ohmic devices include, let's see, well, the other non-ohmic devices, well, they can include a couple. So give me a sec. I'm just, sorry. Okay, so for example, a switch is technically not really a non-ohmic device. It's just because it's sort of just a device. But I will talk about some of them later on. The first one I wanted to show you guys is a capacitor. Now, capacitors are 2 separated metal plates. Now, when I say separated, I don't just mean, oh, they're like, you know, separated. That actually means that there is air between them. The symbol for us, and the symbol actually looks like that. It looks like 2 plates that are separated. Now, what happens with a capacitor? And I find capacitors interesting because you guys, there are capacitors in like so many electronics around your home. What a capacitor does is they build up charge. So if you've got, let's just draw a capacitor here. Let's attach a current to it. So let's just say you've got a current goes through here, and what's going to happen is that, let's say that negative electrons move down into this part of the wire, and that's going to push a lot of negative charge here. Now that negative charge can't get anywhere, can't conduct, because it's not connected to the other side part of the wire. But what can happen is, even though it's not connected, you can actually end up with a buildup of charge. You could actually end up with a lot of positive charge on this part of the wire. And so what you end up with is you end up with I guess there's one way you could think about this, is you could call this a charge bank. Now what happens with this charge bank is that when you, they release the charge in a short pulse of high current. So if I took this now charge bank, right? Let's just say I turned off the voltage. If I turned off the voltage, all of a sudden, what's going to happen is I'm going to have a bunch of now electrons all gathered in one place. And all these electrons that are all gathered in this one place, they're going to say, well, I don't want to be here anymore. There's no reason to be here. There's no current, so I'm going to leave. And all of that charge leaves all at once. And so you get a short pulse of high current because there's a lot of electrons moving. And because all those charges move really, really quickly, they can still travel through the circuit and make the circuit light up or do something. So why do we have these devices? The first thing that I always think about is, I'm like, well, why do we have these devices? The best place, the example that I can give people is the original capacitors were used a lot in cameras. So what a camera would do is it would build up a lot of charge in its flash, right? So if you take a camera flash, what it does is it builds up a lot of charge in the bulb, well, leading up to the bulb, and then just before you want to take the photo, it releases the charge. All that charge produces a high current through that bulb, which makes a really bright flash. And that's how the original capacitors were used. What else can capacitors get used for? Well, they are used a lot in they're used a lot as well in hospitals. They are used in defibrillators. Okay, so if you've ever seen someone with a defibrillator, I've actually was talking about this a couple of lessons ago. When you see those paddles and they charge the paddles up and they say clear, and then they you know, shock someone and they're trying to get their heart rate back. That's then the charging part is actually the charging capacitors. They're putting a bunch of charge into some capacitors and then they're releasing that charge in a very, very short burst. The last thing that though is I will point out is you can see capacitors in a lot of at-home devices. Now, for example, many of you guys may know that if you turn on your TV, it will usually go back to the same channel that you're originally on before when you turn it off. You guys might know when you turn off your laptop, you'll go back to the same channel. You're thinking about this, right? You think, well, if I pull the switch on a TV, right? If I pull the plug on a TV, if I turn it off, it needs to remember what it was doing. So, but if I pull the plug, it's got no electricity. But that's why it's got capacitors for. What capacitors are great for is they can let out a little bit of current, a little bit of electricity the second they're turned off. They're like, in a way, they are like batteries. They hold a little bit of charge. And the reason you can tell that your devices have a battery, next time you are sitting in front of a TV or even the computer and you turn it off, I want you to look at the little red light near the TV. It will go black, but it won't go black straight away. That's because it'll go black slowly. It'll go from red, it'll go dimmer and dimmer until it goes to black, turned off. And that is the capacitor work. The capacitor is slowly letting out charge until eventually it's got no charge left. So it's a really good way of like saving the state of a TV or the state of a computer when your power goes out. Yeah, there is the value. Capacitors are measured in farads for capacitance. And there's a really good video down the bottom here that I usually show students. I'm not going to show you guys today, but if you want to open that up, it is a hacksmith, and he builds a rail gun out of like 20 capacitors. So he builds up a lot of charge, and then he fires all that charge at once, which actually launches a metal ball because it's got like makes a really, really high magnetic field for a very, very short amount of time. But yeah, so that's what a capacitor is. You don't need to know too much about them. You just need to know that they build up charge. One last thing about capacitors. Remember I said that they're very similar to batteries. Well, actually, remember back in the day when I showed you that Leyden jar? We were like, what Leyden jar? When did you show me that? Back at the very, very start, I showed you a Leyden jar, which looked like, too far back, this. A capacitor is a modern form of this in a single component. It builds up charge just like the same way that you build up charge using a Van de Graaff generator or a piece of wool. The only difference is that we're building that charge up in a component, an electrical component. Now, what do they look like? They look like these. Now, if you have a broken TV or a broken computer, and you know it's an electronic problem, a lot of the time it actually is a broken capacitor. What you should do is, if you ever have something broken, you should look for this device here. It'll look like a capacitor. If you've ever pulled apart a computer, you will see that there are these little like dome-like things, and they're attached to sticks. And when they get broken, what happens is that this top part usually expands. So you usually end up with some sort of like thing that looks like that. So what you can do, well, it looks more curved, but yeah, whatever. What you can do is you can actually take that and you can usually replace them pretty easily, and then you can actually get a completely free working TV. I reckon a bunch of TVs are broken around the world just because one small 5-cent capacitor is broken. If you replace that 5-cent capacitor, you can get a whole $200 TV for free. But I actually don't know the actual measurements of that. But just, yeah. So those are capacitors. We'll talk briefly about resistors. Resistors are just, we've already talked about resistors. We know what a resistor is, just so that we know. Resistors can be measured in ohms. These are ohmic devices. They follow Ohm's law. Their symbols look like this and this. Resistors are non-polarized, as opposed to diodes. Resistors, you can put them in any way you like. You can put them in like this. You can put them in like this. As long as they go in the circuit, it doesn't matter. The main reason I wanted to show you guys this slide is I wanted to show you guys this over here. This is a way that you can look at a resistor and you can read what type of resistance it has on it. Every resistor should have some very, very tiny bands. And if you use those bands, look at those bands, and you use this code, you can figure out how many ohms that resistor has, and also how close it is, whether it's got an error of 1% or whether it's got a big error of about 10%. You can see that looking at the bands. I hate doing this though, because the bands on a resistor are so small. I have glasses, I can barely read them. So you might, like when I show you a picture of them, you guys will be like, oh, I can see that easily, but yeah, usually you can't. So resistors are ohmic devices, but yeah, like, and also one more thing, it's interesting that the Europeans and USA have different ways of drawing resistors. I think I've told you this, but I use both interchangeably. I do like the USA one because that's sort of, as I said, how a resistor would be made. It would be a long piece of wire that would get coiled up. That's how resistors used to be made. So that sort of makes sense. Resistors aren't really just boxes. I think they use boxes in Europe because ultimately there are a lot of resistors in circuits. So it's good just to draw them. So that's resistors and capacitors. Let's talk about special types of resistors. Oh, we're getting fancy now. Now, some components do change their resistance depending on conditions. These are a thermistor. So a thermistor is has resistance change depending on temperature. That makes thermistors really great for measuring, well, pretty much anything where you need to know the temperature. You might use it in a heating cooling unit. You might use it in if you've got a self-heating, if you've got a sous vide machine that heats up steak for you, then you might use it. If you've got a hot water bottle, like an electric blanket that automatically switches off when it gets to a certain temperature, these will have thermistors in them. A lot of 3D printers have thermistors in them to make sure they don't overheat. So thermistors are great. All they do is they measure the temperature. What do they look like? The symbol for a thermistor is down here. I don't know why it's just a line that goes across it, but it is just a line, a bent line that goes across it to make a thermistor. A photoresistor is a light-dependent resistor. Light-dependent resistors mean that as light falls on them, they will conduct, their resistance will change. These are great for, well, actually, you know what? I'm going to open this up. Can someone tell me, either in chat or out loud, what kind of device do you think would have a, what kind of device do you think would have what are we talking about? Sorry, what kind of device would have a photoresistor in it? What kind of device would be really useful that we would need one? Solar panels, great idea. Solar panels, you would need if we want to try and track where the sun is, then you might use oh, look, the light's coming from this direction, so let's change the angle of the solar panel. What's another device that would use a light dependent resistor? What's another device we need to measure the light of something? Pog. Camera. Camera will be good. Camera's a good one. I like camera. Who said camera? Reese. Good job, Reese. Camera is good because, for example, if you're trying to take a photo and you're like, oh man, if you've got a light, if you've got a diode here, what it can do is it can, sorry, not a diode, a photoresistor, is you could have it then say, oh, given the light conditions, we suggest you use a flash. So that means, yeah, your camera will probably, and this includes as well on a phone, it's probably going to have a light-dependent resistor on it. What else have we got? Have anyone got any other suggestions? Let me just open up chat. Anything else? Can you give me one more? What's another place you would use? We could use a light-dependent resistor. Auto brightness on your phone. Yeah, I like that. That's another place. Yeah. These are all good suggestions. I might let's write that down. Auto brightness. What I might talk about is, like, for example, we could have a night light. So if you've got little kids that are afraid of the dark, maybe when it gets dark, the light comes on. Night lights are great for that. So they would, they can, using the resistor, can detect when it gets too dark. And I guess there might be one, I guess we could talk about night lights. What else can I think of? Oh, automatic doors, believe it or not. Some automatic doors, these are really old ones nowadays. They now sort of replace them with motion sensors, which I think have this kind of device in them, but it's not the same. What old automatic doors did, and they still sort of, you still can see them, is you would have a laser light, and the laser would shine onto a photodiode. And the idea is when that line got broken, so if a person was standing here, if that person was standing there, they would break the laser. That would tell the photodiode, oh, there is someone standing at the door. And so it would then open the door, and the door would like open to the right, and then you would walk through. And then when you stop breaking it, it would then open up again. So those lasers still, like, there are still doors that do that, but I don't see them around very often. Nowadays, the most common one that I see for doors are just like those little silver balls on the top of doors that just measure how you're walking towards it. But back there used to be more laser ones. I used to remember because I think when I was younger, I used to be like, oh, can I climb over this laser line, like, do a James Bond kind of thing without setting off the door and, the alarm that, usually you just accidentally bump into it because it's an invisible laser, you can't see it. So these are the resistors that I said, the special types of resistors. I've already just talked about them here, so I'm not going to talk about them again. Resistors do come in a variety of ratings. There's no pencil here, so I just wanted to talk about this. Sometimes you will need really, really big, thick resistors because you're dealing with really, really high currents and really, really high voltages. But most of the time, you can probably just get away with small resistors because you're just dealing with 2 or 3 volts or something very, very small. And yeah, the last couple of things I want to talk to you guys about. Do I expect you guys to memorize these? No, but I just wanted to show you, these are a bunch of extra symbols that you can use. We've got it, by the way, remember I was showing you earlier, this is the LED symbol. So here is the LED symbol here. And then I've got, here's the light dependent resistor. So that's the symbol that I just showed you before. We've got thermistor, capacitor, some weird ones that we made that you guys haven't seen before include the microphone. We've got a variable resistor. Remember, so a variable resistor is kind of interesting. It's going to be able to change the resistance of something. Let's just say you want your resistor to be 10 ohms, and then, no, actually, you know what? I changed your mind. I want it to be 30 ohms. You can change that with a variable to resistor. That might be really good for a situation where you're like, oh, I'm trying to, if you have something like that measures, like let's just say you're trying to use a dimmer switch on a light bulb, you might want to turn the switch on and off to make it darker or lighter depending on that. We've got a loudspeaker, we've got a lot of these you've seen before. These are DC power supplies and another one, but yeah, these are all these extra components. Ladies and gents, that's it. That's all I wanted to talk to you guys about. And I don't want to talk anything more because I already chewed your ear off yesterday by speaking for way, way, way too long.